Thank you. Okay, so I'm going to be talking today about True2F, our system for backdoor-resistant authentication tokens. This work was done at Stanford and at Google with Henry Corrigan-Gibbs, David Mazieres, Dan Bonnet, and Dom Rizzo. So as you're probably all aware, hardware authentication tokens are a particularly effective form of second-factor authentication, with U2F tokens being especially popular. Since Google mandated over a year ago that all its employees use these security keys, they haven't discovered a single instance of corporate credential theft, showing just how effective these tokens are. So the U2F protocol runs in two stages. So the first stage, registration, is run when a user wants to associate their token with some account. So the server sends some identifier to the token then generates some server-specific ECDSA key pair and sends the corresponding public key back to the server. The second stage, authentication, is run when a user wants to log into their account. So the server sends some identifier along with a challenge to the token signs this challenge using the key pair it generated at registration, and sends the signature back to the server for verification. So in this way, U2F provides a really strong defense against phishing attacks, as well as browser compromise. So in particular, even if malware takes over your browser, it can't authenticate without interacting with the token. We get this really strong defense against external adversaries because only the token knows the cryptographic secrets. But what about vulnerabilities in the token itself? So we might not be entirely comfortable trusting the token with our cryptographic secrets for two reasons. So first, the token might have some implementation bugs. And second, it might be subject to supply chain tampering. Implementation bugs are a very real problem. So in 2017, a bug was discovered in the Infineon random number generator, which affected a wide variety of products, including Estonian smart cards, Chrome TPMs, and the YubiKey PGP functionality. Just last week, a bug was discovered in the Google Titan security key Bluetooth stack. And all these bugs just show just how fragile these secure hardware elements are. Supply chain tampering is another problem. We know from the Snowden leaks that these types of supply chain attacks actually happen. On your left, you can see a photo of the NSA installing implants in Cisco routers. And we know that users are actually concerned about these types of supply chain attacks. Last summer, when Google released the Titan security key, there were calls for greater transparency into the supply chain process. So not only do these attacks actually happen, users are actually concerned about them as well. So to address both these security threats, we introduced True2F, which provides the same protections as U2F, while additionally protecting against faulty tokens. So just as in the case of U2F, True2F addresses the case where the browser is malicious. So the browser doesn't learn any secrets through its interactions with the token. However, True2F additionally protects against faulty tokens. So to address the case where the token is malicious, the browser enforces the correct behavior of the token to prevent the token from leaking secrets through protocol messages. So in this way, True2F addresses the case where either the browser is malicious or the token is malicious. So we have three primary design goals. So the first is to augment U2F to provide a strong protection against faulty tokens. So you want to have the same protections as U2F, even if the token is buggy or backdoored. Second, we want to do this in a way that's backwards compatible with existing U2F servers. So this should only require changes to the token and the browser, but not the server. And this is important for real-world deployment, as it's not very feasible to go out and change every single server running the U2F standard. And finally, we want this to be practical on commodity hardware tokens. And we implemented and evaluated this on Google hardware. I'll be showing you that later. So to achieve these three goals, we adopted the following two design principles. So first, both the browser and the token should contribute randomness to the protocol. And this prevents the token from using some bad source of randomness. Second, the browser should be able to verify all deterministic token operations. And this is important so that the browser can check the token's behavior. So as I mentioned, we also implemented this on Google hardware, and I'll be showing you the evaluation results at the end of this talk. So the U2F protocol has two steps. And in True2F, we're going to add an additional step, initialization, which we run after purchasing the token and before registering with any site. We're also going to modify the registration and authentication steps. I'm going to walk through each of these protocol steps, and I'm going to start off with initialization. And here, the idea is that both the browser and the token should contribute randomness to the protocol. So at a high level in initialization, we want to run some collaborative key generation protocol between the token and the browser, at the end of which the token holds the master secret key and the browser holds the corresponding master public key. It's important that we generate this key pair collaboratively. So we don't want the token to generate this on its own because the token could be using some bad source of randomness. We also don't want the browser to be generating it on its own either because we don't want the browser to ever know this master secret key. This is why we need collaborative key generation. So we want the following two properties from this protocol. So first, the token shouldn't be able to bias the master public key that the protocol produces. This is important if the token has some bad source of randomness. And second, the browser should learn nothing about this master secret key. So the cryptographic secrets should remain entirely on the token. There's actually a protocol that already does this by Cork and Gibbs et al. However, it's pretty slow on the small embedded device that we're working with. And so we present a protocol that reduces the number of group operations by about 3x in comparison to their protocol, which greatly improves the performance. And I'm not going to go through the protocol in detail right now, but you can see our paper for details if you're curious. So that's initialization. I'm now going to move on to registration. And here, the idea is that the browser should be able to verify all deterministic token operations. So just as a reminder, in U2F registration, the server sends some identifier to the token. The token then generates some server-specific ECDSA key pair and sends the corresponding public key back to the server. So we can imagine some implementation bug that undermines the security of registration. So for example, the token could generate this key pair using some weak source of randomness. So now if the attacker has this public key, they're actually able to learn the original secret key. We can also imagine supply chain tampering undermining this step. So let's say some attacker who manufactured your token is able to get you to register at evil.com. So now the token is going to choose some public key for evil.com that hides information about the secret key for another site, maybe the secret key for github.com. It sends this bad public key back to the server, and the server is now able to extract information about the secret key from github.com from this bad public key that it receives. So in this way, the token has managed to exfiltrate secrets that were never supposed to leave the token. So to address both these security threats, we introduced this new mechanism we call verifiable identity families, or VIFs. And these VIFs are going to leverage the master key pair that we generated at initialization. So you might be wondering, well, why can't we just use the same collaborative key generation mechanism that we used for initialization? Well, the problem here is that these tokens have a very small amount of storage space, and we don't want to bound the number of sites that you can register with. And so we want to be able to derive this key pair whenever we need it, instead of storing the secret key on the token. And these VIFs allow us to derive server-specific key pairs in a deterministic and verifiable way from a single master key pair. It's also important that these key pairs are server-specific to provide unlinkability between sites. So in our paper, we formally proved that these VIFs are unique, verifiable, unlinkable, and unforgeable. I'm not going to go into the details about these definitions now, but I'll show how the simplified construction achieves these properties. And so now I'm going to walk through a simplified, weak version of the VIF construction. I'll hint at why this is weak and why we need the full, and what the full construction of the paper looks like, although, again, check out the paper for details. So here we're going to use some group G, a prime order Q, in this case, the NIST P226 curve. And, I'm going to rewrite the master secret key on the token and the master public key on the browser as X on the token and big X or G to the X on the browser. We're then going to use these values to compute this key K, which is just the hash of big X. And so now I'm going to walk through the simplified protocol. So here, the server sends some identifier to the token. The token then computes this value alpha, which is just the PRF keyed with K of the server identifier. The token is then able to compute the server-specific secret key, which is just alpha times X, and the server-specific public key, which is G to the alpha times X. The token sends this public key back to the browser. The browser can then also compute alpha and check that the public key correctly incorporates alpha. So the public key should be of the form big X to the alpha. If this is the case, the browser knows that this public key was correctly formed and so can send it back to the server. So the first property we wanted is uniqueness. So the token should be able to produce the unique key pair for this site. And here we get this property because this value alpha is unique for every server. It's just the PRF keyed with K of the server identifier. The second property we wanted is verifiability. So the token should be able to prove to the browser that the public key it receives is really the unique public key for that site. And we get this property because the browser is also able to compute alpha and check that the public key is derived using this value alpha. Third, we want unforgeability. So the browser shouldn't be able to forge a signature under the public key it receives. We proved this formally in the paper. And finally, we want this notion of from the simplified construction, we get this notion of weak unlinkability. So the server shouldn't be able to distinguish the public key it receives from a random ECDSA public key. And we get this property because the server doesn't have this key K and so can't compute alpha and see that the public key it receives are all derived from the same master key pair. However, this simplified construction does not provide full unlinkability. We define this more formally in our paper, but informally, this just means that the browser shouldn't be able to generate public keys without interacting with the token. And so the full construction they present in the paper uses verifiable random functions to provide this property. So that's initialization and registration. I'm now going to move on to authentication. And here, the idea is that both the browser and the token should contribute randomness to the protocol. So just as a reminder, in U2F authentication, the server sends some identifier along with a challenge to the token. The token is then going to sign this challenge using the key pair it generated at registration and send the corresponding signature back to the server for verification. So we can imagine an implementation bug that undermines the security of authentication. So for example, the token could choose the signing nonce with a weak source of randomness. And so with enough of these signatures, an adversary can actually recover the original signing key. We can also imagine supply chain tampering undermining this step. So for example, the token could hide the secret key for another site in the signature. And this is possible because there's randomness chosen by the signer in ECDSA signatures. And so both of these would not be problems if we could use some unique signature scheme like BLS or RSA full domain hash. However, we're tied to ECDSA to maintain backwards compatibility with existing U2F web servers. And so we need some way of controlling the randomness in these ECDSA signatures. And so to do this, we introduced this new mechanism we call firewalled ECDSA signatures, based on previous work on some cryptographic reverse firewalls. So I'm not going to go through the construction in detail, but it's motivated by the following two ideas. So first, the token in the browser should use collaborative key generation to generate some signing nonce. And then second, to handle ECDSA malleability, signatures should be re-randomized by the browser so the token can't leak information through which signature it chooses to send. You can see the paper for details. This is based on previous work on subliminal free and subvergent resistant signature schemes. So gone through all the True2F protocol steps now. There's some other contributions in the paper I don't have time to discuss now, including cryptographic optimizations tailored specifically to the token hardware, and a flash-optimized data structure for storing U2F authentication counters. I just want to touch on one implementation note as well. So U2F doesn't require the browser to keep track of any state. However, True2F does require the browser to know this master public key to check the token's correct behavior. This then introduces the problem of, well, what happens if you're using one U2F key with multiple browsers? So one simple way to address this is every time you plug in the token just gives this master public key to the browser. And this provides some basic protection against implementation bugs, but isn't very satisfying if you have a malicious token, as I could just give the wrong master public key value. And so a stronger solution would be to actually sync this master public key across browser instances. So we also implemented True2F on Google hardware. On your left, you can see a Google development board running True2F. That's where we got the evaluation numbers that I'm about to show you. And on your right, you can see a Google production USB token with the same hardware specs, not currently running True2F, but capable of running it in the future. And so when we first started evaluating True2F, we knew that there would be some overhead in comparison to traditional U2F. And so our goal was to reduce this overhead as much as possible. And so here you can see the authentication protocol latency. And we can see without any optimizations, True2F is pretty expensive in comparison to original U2F. So 446 milliseconds in comparison to 23 milliseconds. However, as we introduce a variety of optimizations, we can actually reduce this overhead to 57 milliseconds in comparison to 23 milliseconds. So True2F is only about 2.5 times slower than traditional U2F. Registration looks pretty similar. I'm just focusing on authentication here because it's the common case. We were also curious what latency the actual end user experienced. So here we measured the time from when the browser receives some request to when the browser is able to respond. And we found that the user doesn't actually experience this 2.5x slowdown. A lot of time is being spent on the browser middleware as opposed to doing the crypto on the browser and on the token. And so the end user is actually only experiencing an additional 20 to 30 milliseconds of delay. And so True2F is only about 12 to 16% slower than traditional U2F. It's also important to note that normally you have to tap these tokens, and we instrumented the tokens to not require this touch for these tests. So in conclusion, True2F shows that we don't need to settle for untrustworthy hardware. True2F augments U2F, provides strong protection against backdoor tokens in a way that's backwards compatible with existing U2F web servers. True2F is also practical to deploy in that it's performant on commodity hardware tokens. We'd love to get True2F out to real users. We've talked a little bit with the FIDO standards body, which is responsible for the U2F standard, and we'd love any help getting True2F out to real users. You can see the paper link and the code are all online. Thank you, and I'll take any questions.
Hello, hi, it's Marco Corvas from University of Edinburgh. So great work. I think especially the backward compatibility is very useful. So I have one question. So well, it's like a comment. So I think there's still some trust in the device, because if the master secret key would be available to an attacker, of course there would be no security. So one question is, if you would be willing to give up this backward compatibility, could you potentially do better?
So we actually don't. So the token does not come pre-initialized with this master secret key. So once you get this token, you can actually run this initialization procedure, and our protocol guarantees that the token can't leak information through these protocol messages. The token has no way to exfiltrate this master secret key.
No guarantee that there isn't some kind of biased randomness used for the master secret key.
So actually, I didn't show the protocol here, but it's actually using randomness from both the token and the browser. And so at the end of this protocol, the token is holding some master secret key, and the browser is holding some corresponding master public key. And so if you're curious, you can check out the paper for how we do that. But actually, it ensures that it's using randomness from both, so it can't use some bad source of randomness. That's a great question.
I have a question. Do you have a sense for whether True2F would have defeated the recent Bluetooth attack that Google disclosed?
Yeah, so the Bluetooth attack was related specifically to the Bluetooth stack, so it didn't affect the USB and NFC tokens. And so I don't think it would have affected that, to my knowledge, because it was related to because it was related specifically to the Bluetooth stack as opposed to like the protocol messages that were being sent.
So I have a question about how you think about plugging this potentially untrusted device into an USB port.
This is a great question, and that's a great question. So yeah, obviously, plugging in a potentially untrusted device into a USB port is like already a problem, and we consider our work to be sort of orthogonal to those types of problems. And we're looking specifically at protocol messages and making sure that you can't leak information through the protocol messages. And we think there's like a lot of other great work on trying to make it safer to plug in these USB devices. And so we discussed some of that related work in the paper, but that's not specifically what we're focused on right now. Although you're totally right that that's a really very real problem.
Hi, very basic question. Is there a way to distinguish if someone has sent you a U2F token or a True2F token? Like if I think I'm buying a True2F and then someone just swaps it out with a compromised U2F.
Yes, this would be, you would need support for this in the browser to give sort of some indication that you're using some, the browser thinks it has some True2F token, and so it's doing all the checking correctly, and it's not, just switching to U2F. That's a great question. I think that would be, that would be an implementation consideration. Yeah.
All right, let's thank Emma again.